solving this problem called binomial coefficients. So our task is to calculate n binomial coefficients modulo 1,000,007,000. So a binomial coefficient AB can be calculated using the formula a factorial divided by b factorial times a minus b factorial. And we assume that a and b are integers and b is greater than or equal to 0 and smaller than or equal to a. So the first line of the input will contain an integer n up to 10 to the 5th, then will follow n lines, each containing two integers a, b, both up to 1,000,000. And each time we will have to print the binomial coefficient. So let's head to the drawing board and see how we can solve this problem. So we need to calculate the binomial coefficient that we represent by this. And we were told that this was equal to a factorial divided by b factorial times a minus b factorial. And if you recall from the previous problem, this was equal to CA choose B. So the number of ways of choosing B elements from A elements is precisely equal to this. And these values are very famous in mathematics. They are involved in a lot of formulas. And they also appear in Pascal's triangle, which is a very famous triangle in mathematics. So this is Pascal's triangle and it contains all binomial coefficients. So we can perceive Pascal's triangle as having many rows and each row contains many columns. So for example, this is the second row. We are starting from 0, so this is 0, 1, 2. So this would represent C of 2, and here we are just choosing 0 elements. So if we choose 0 elements from 2 elements, we have one way of doing that, precisely not choosing anything. And this would represent C of 2 choose 1. So we are choosing 1 element from 2 elements, and this is equal to 2. For example, if we have 2 elements A, B, we can either choose A or choose B. And finally, this represents C of 2 choose 2. And there are exactly one way of doing so. So if we have 2 elements A, B, and we need to choose 2 elements, our only choice is to pick A and B. And a lot of properties that involve binomial coefficients can be read from this triangle. For example, we might sum the values in each row. For example, here we will have 1, here we will have 2, here we will have 4, here we will have 8, here we will have 16, and so on. So you can notice that the sum of all these values is always a power of 2, and this makes sense. So we know that the total number of subsets of n elements is equal to 2 to the n. And we can also reformulate the total number of subsets. So the number of subsets of n elements, the number of subsets of size 0 plus the number of subsets of size 1 plus the number of subsets of size 2 all the way up to the number of subsets of size n. And what is the number of subsets of size 2 from n elements? Well, it is precisely equal to choosing 2 elements from n elements. And if we sum up all these values, it's gonna represent the sum of Ci choose n from I equals 0 up to n. And since these two definitions are equivalent, then this will be equal to 2 to the n. Another interesting property of Pascal's triangle is that we can obtain any value by summing up the value on top of it and the value to its left. So for example, 3 is equal to 2 plus 1. 21 is equal to 6 plus 15. 35 is equal to 15 plus 20. And we can formulate this observation in the following manner. So C of B choose A is equal to C of B minus 1 choose A plus C of B minus 1 choose A minus 1. Another interesting property of Pascal's triangle is called the Holistic Theorem. So if we start from any position on the boundary here and we go down any number of steps we want, then we move once to the left, like forming a hockey stick, and we sum all these values, then they're gonna be equal to this value. So we can try here. So 1 plus 5 is 6, 35 plus 15 is equal to 50. So 50 plus 70 is 120, plus 6 is 126. And this works all the time. So if we sum these values here, we're gonna have 120 plus 36, so that's 156, plus 8, so that's 164, plus 1, so it sums up to 165 as we stated. And we can formulate the Holistic Theorem in the following manner. So the sum from I equals 0 to k of CB plus I choose I is equal to CB plus k plus 1 choose k. So maybe in some theorem you might have a for loop that goes from 0 to k summing up these values, and instead of looping through all these values you can just calculate this in O of 1. And finally, there is an interesting relationship between Pascal's triangle and Sierpinski's triangle. So if we take each value in our triangle and calculate it modulo 2, we either gonna get 1 or 0. For example, here we will get 0. And in other words, if we go ahead and highlight all the even numbers in our triangle, we will get the following. So Sierpinski's triangle is a fractal that looks something like this in blue. So it starts with a triangle, then it finds the midpoint of each side, then it removes this area, then it works on recursively on the other triangles, and it keeps going like this ad infinitum. And if we went ahead and colored the even values in a different color, we will find the same pattern emerging here again. So you can see that the gaps in our triangle here match with the even numbers. And this might seem magical at first glance, but if you think about it, all the rows that represent a power of 2 like 2, 4, 8, and 16 for example, all will be divisible by 2. And we said that for each value we can get its value from the value on top of it and the value to its left. So for example here we had one value that was divisible by 2. Now, next we have 3 values that are divisible by 2, and on the next row we will have 2 values because both of these will only be calculated based on the 3 values that were already even. So we'll have a 3 to 1 pattern, then here we will have a 7, 6, 5, 4 and so on pattern. And this explains why for certain rows all the values are divisible by our mode. And this property will lead to the emergence of this triangular pattern, and we could argue similarly about rows that are only divisible by 2 but are not powers of 2, and they too will form this interesting triangular pattern. So we diverge too much from our problem, but I think these are interesting things to say about binomial coefficients if it is the first time you're gonna get introduced to them. So as we said, the binomial coefficient AB is equal to A factorial divided by B factorial times A minus B factorial. So the only challenge here is that these values will be very large, and that's why we need to calculate them modulo some prime number. And if we only had multiplication or addition, it would be fine, but here we have division, and as we know, A divided by B mod P is not equal to A mod P divided by B mod P. So for example, 6 divided by 2 mod 2 is equal to 3 mod 2, which is equal to 1. Whereas if we were to calculate it this way, we'll get 6 mod 2 divided by 2 mod 2. And 6 mod 2 is 0 divided by 2 mod 2, which is also 0, will give us an undefined form. So we deduce that this formula is not correct. However, as we saw in previous videos, there is a very powerful theorem that comes back again and again, and that's Fermat's little theorem. And it states that A raised to the P minus 1 is congruent to 1 mod p if the GCD of A and P is equal to 1. And we can break down this formula to get the following. So we can separate an A here to get A times A raised to the P minus 2, and that would be congruent to 1 mod P. And from this formula we can deduce that A raised to the P minus 2 is the modular inverse of A, which means that if we multiply A by A raised to the P minus 2, we will just get 1. And I'm not gonna be very rigorous in what I'm gonna do next, but just take my word for it. So we can actually multiply here by b factorial raised to the p minus 2, both on the numerator and the denominator. And this will give us b factorial raised to the p minus 1 factorial. And we just saw that that was congruent to 1 mod p. So basically this just becomes 1. And we can actually do the same thing with a minus b factorial. So if we multiply this by a minus b factorial raised to the p minus 2, both to the numerator and the denominator, we will get a minus b factorial raised to the p minus 1. And this also is congruent to 1 mod p. So basically we just got rid of our denominator, and all what we are left with is the product of these three quantities. And to calculate a factorial, we can do that recursively, so we can just store these values in an array, and we can just say that fac of 0 is equal to 1, then fac of I will be just equal to fac of I minus 1 times I. And the total complexity in this problem depends on both n and 10 to the 6th, n being the number of queries we have to answer, and 10 to the 6th being the largest value we may have to calculate the factorial for. So with some pre-processing, we can just answer all queries in O of 1, so our total complexity may be just O of n, since we have to answer n queries, plus the complexity of the pre-processing, and since we have to go up to 1,000,000 to calculate the factorials, and since we have to perform a binary exponentiation here, our total complexity for this will be 10 to the 6th times log of 10 to the 9th plus 7. So that's pretty much it. Let's go ahead and check out the code now. So this is our program. Since binomial coefficients come back time and time again, and since factorials do that as well, I'm gonna actually code this as a structure or as a class. I will just use a structure so I don't have to declare things as being public. In a struct they are public by default. And I'll call my struct factorial, and it will have the following attributes. So it will have a vector of long to store the factorials. It will also have a vector of long to store the modular inverse of that factorial. I will also have an attribute for the actual value of the modulo, so I can use this struct even if the modulo is different in other problems. Then I will have an inner function that is the modular binary exponentiation. So I can just copy this without having to copy in this as well. And if you recall from the problem exponentiation, this function calculates a raised to some power b in log of b. So in the modular exponentiation function, we had the following. So this was our base case. If the exponent is equal to 0, we'll just return 1. Then our result was just calculated as being our base raised to the exponent divided by 2. And we had two cases. If the exponent was odd, then our result will be result times result time base, because for example if we wanted to calculate 2 to the 5th, then 5 divided by 2 would give us 2. So if we calculate 2 squared, then in order to calculate 2 to the 5th, we will just multiply 2 squared times 2 squared, and since 5 is odd, we will multiply it by 2 one more time. And if the exponent is even, we'll just return result times result. Now I'm gonna introduce my constructor. So it's gonna take two ints, the first one being the largest value of factorials I will need to calculate, and the second one being my modulo. Then I will resize my two arrays to have size n plus 1. Then I will set my modulo to modulo. And now I'm gonna initialize both factorial of 0 and inverse factorial of 0 with 1. And as I said, I will calculate factorial and inverse factorial recursively. So I calculate factorial first. So factorial of I is just I times factorial of I minus 1. And the inverse factorial is just factorial of I raised to modulo minus 2. So that's pretty much it. Now all what I have to do is write some getter functions. So I will write a getter for the factorial of int x, which will just return factorial of x. I will also write one for the inverse factorial of x. And finally, I will write one for the binomial coefficients of a and b. And as we said, this was just equal to factorial of a times the inverse factorial of a minus b times the inverse factorial of b. And we will extend this structure later to contain more combinatorial formulae. And for now, that's all what we're gonna need, so we can write a pretty clear code for our program. So now let's answer the queries. So we'll start by reading n, then we will create our object factorial, and the largest factorial we would wanna know is up to 1,000,000, and our modulo is 1,000,007. Then we will answer the queries. So for each query we will read a and b, and we will just output the binomial coefficient of a and b. So that's pretty much it. Let's go ahead and submit. So that worked. Thank you for watching. See you in the next video. Bye bye.